In this session, we're specifically going to discuss B-mode imaging, as this is the workhorse of ultrasound imaging, and this is the key topic that we need to cover. So we're going to start by talking about the pulse characteristics, then the B-mode display, and then the types of artifacts that you encounter in B-mode imaging. So remember that we assume our pulse speed is always 1540 meters per second. Typical spatial pulse lengths are of the order of 2 to 5 wavelengths for B-mode. The wavelength is typically 1.5 millimeters at 1 megahertz and drops to 0.15 millimeters as the frequency increases to 10 megahertz. And the pulse is damped. So remember, we saw that the pulse shape has this sinusoidal oscillation, which is inside the envelope of an exponential decay. Now, we're going to see that we have to do a series of pulse processing steps. And the first of these is called amplification. So the wave packet that's emitted into the patient and then comes back is going to come back, and it's going to be significantly attenuated. So in order to get decent signal, we're going to amplify that signal. So once we've applied the amplification, which is going to convert the received waveform into something which is going to be in millivolts as opposed to being in of a much smaller amplitude in microvolts, we're then going to see we need to convert this sinusoidal shape in a damped envelope. We want to get from that effectively to a step pulse that we can digitize, which gives us a number that's representative of how strong the reflection of that wave was. So that's going to be our goal, to go from this oscillating waveform that covers an expanse of time and convert that just into a single number which tells us how strong that reflection was. And we're going to see the steps we use to do that are called rectification, demodulation, and then transformation to a gate pulse. So the easiest way to discuss this is in terms of the diagram at the bottom of this slide. So we can see the input signal oscillates above and below the baseline. So it has positive and negative components. And all of those components are indicative of what happened to the outgoing pulse to give us that returning pulse. So we need to capture all of that information in order to give us the total energy that was reflected back to the transducer. So if we just integrated that pulse, the positive parts and the negative parts would cancel out, and we'd get a very, very small number. And so clearly that's wrong. What we want is the total area contained within both the positive and the negative components of that pulse. So the first thing we do is what's called rectification, and all rectification means is keep the positive parts positive and also make the negative parts positive. So you can see the next waveform there is a form of the first waveform, but it's all positive. So the next thing we need to do is then capture the total area of that pulse, and the way we do that is called demodulation. So the demodulation processing algorithm then converts that envelope, converts the pulse there into an overall envelope, and so the total area within that envelope is then what we're going to convert into the final step pulse. So the step pulse is that square pulse or rectangular pulse at the end there, and the height of that is proportional to the area inside the demodulated envelope. Right, so some important considerations in terms of processing electronics, the first of which is noise. Clearly we want a low noise system. The second of which is the dynamic range. So the dynamic range defines how sensitive our electronics are to the system, to the input effectively. So you can imagine if we had a thermometer that was measuring the temperature of something, So say we were in the Sahara Desert. We would want we know that the temperatures are going to be high, so we want a system that is measuring temperatures from, say, 10 degrees up to 50 or 60 degrees. And we would want that in reasonable resolution. So we wouldn't want to go, we probably wouldn't want to go in 5-degree steps, because the resolution of that thermometer would be very inaccurate. But at the same point, we wouldn't want to go in steps of 0.00001 degree, because those steps are unresolvable to us as humans. So the dynamic range calculation takes into account both of those effects. It takes into account the length of the range. So clearly there's no point in our range going to minus 60 degrees, because in the Sahara Desert, we're not in Finland, we're not in near the Arctic Circle, we're not going to get temperatures of minus 60. And also we want to go in high enough resolution steps that we get a sensible number. So here we can see both of those factors are included in the dynamic range calculation. So S max minus S min is the range, so that would be the maximum temperature to the minimum temperature, and delta S would be the temperature steps. So in the same way, just to confirm that we're applying that to voltages with respect to the treating of ultrasound pulses. So one of the next steps of correction we have to do is a form of logarithmic amplification. Now in ultrasound, logarithmic amplification can be applied at multiple points, but the first one that we're going to discuss is called time gain compensation. So we've seen previously that the amplitude of the returning echo isn't necessarily, so the strongest returning echo isn't necessarily from the highest reflection, sorry, the strongest reflection. So if I've got some bone at some depth, that's going to be my strongest reflector. Now, if that bone is close to the transducer, I'm definitely going to get the strongest reflection from that bone. But as that bone migrates deeper into the patient and further away from the transducer, when I transmit my ultrasound energy, that energy is attenuated by everything that's in the body before it gets to that bone. So by the time that energy gets to the bone, it would be a much smaller fraction of what it was when it was originally emitted from the transducer. And then when it's reflected, it has to come all the way back again. And that reflected energy is going to also be attenuated on its journey back to the transducer. So just because an echo is coming from a strong reflector doesn't mean it registers as a strong reflection on the transducer. In order for that to occur, which is indeed what we want to occur, because if there's bone there at a depth, we want to know that it's there at a depth. What we need to do is apply a correction for the fact that as the deeper something is in the patient, the weaker its reflected echo is going to be because of the attenuation of that energy. And that's called time gain compensation. So our time gain compensation uses exactly the words in the way they're structured. So gain means amplification. So we use an amplification factor that is proportional to the time it took for the echo to come back to the transducer. And in that way, we ensure that our strongest reflected signal is from where it should be. So it's from an interface which occurs as a strong reflection. Okay, then once we've done all of this processing, we then have to display that intensity. So our step pulse that we have after those initial steps is going to have a height that was proportional to the area of the pulse. We've applied our time gain compensation correction to scale that appropriately for the depth at which that occurred in the patient. And then we have to take that number, whatever that number is, and convert it into a color. So we're going to color the pixel, and remembering that the pixel identity comes from the depth of the interaction, which is calculated from the time difference. So we start the stopwatch as soon as the pulse is transmitted into the patient, and we stop the stopwatch as soon as we get a reflected echo. That gives us the depth of the pixel, and we know the lateral position of the scan line because we know which bank of elements we group together to form the aperture, and we assume that the center of that aperture is where the scan line occurs in the display. So we know the line position, and we know the position along that line, which is the depth, and we then need to, that square that's identified, we then need to color a color between black and white. And so we use 256 colors. So the human eye can't resolve any more than 256 colors. We could have 20,000 shades of grey between black and white, but there's no point in dividing the scale up into that many small blocks. That going back to our dynamic range argument, because the human eye can't resolve all of those subtleties between black and white, so there's no point in wasting all of that processing. So we settle on 256, which gives us enough enough gradient from black to white to deal with what the human eye can cope with. Now, those numbers are encoded on a data string, which is processed by electronics in the ultrasound system. And so we can see we have the scan line number, which is recorded first, so that's the number 10, so we've assumed it's scan line number 10. And the position along, so we've assumed that there are 400 pixels, so we can see that the numbers go from 0 to 399, and then each one of those has a voltage pulse, which is going to be represented as a colour from black to white, from 0 to 255. Right, so once we've got the display and we're looking at the display, we have to try and understand what it is we're actually looking at, and that's where a significant portion of the training in ultrasound comes in. So if I give a child an X-ray image, a small child would be able to tell me roughly what the different parts of the X-ray image show, because it's very intuitive to look at an X-ray image and see and correlate that with our knowledge of human anatomy. Now, for ultrasound, it gets a lot more complicated, because not only do the images look different because of the shape of the transducer and therefore the shape of the display, but also sound bounces around a lot more than X-rays. And when I say bounces around, I'm talking about those effects of refraction and diffraction. So because sound changes direction and changes path, we also get significant artifacts as a result of that. So we can see various forms of shadowing artifacts. So when we've got transitions between highly reflecting tissues, we're going to get shadowing artifacts. Now, one thing that we have to account for is that when we set our depth marker, our depth cursor, on the display, the focal depth point, in order to reduce those artifacts, has to be at the right depth. So we can actually flip that argument around, and we can use movement of the focal depth position in order to gain an understanding for whether or not we're really seeing an artifact or not. So there are various different forms of shadowing artifacts. We can also get refraction at the edges of objects, which again changes direction. Because the beam is focused and is changing shape, we get beam width artifacts and slice thickness artifacts. So the size that we measure of an object has to take into account the combination of the true size of that object with the beam width at that location in the scan. We also get lobes. So the beamformer that's used in ultrasound, its optimization aim is to force as much of the sound energy along the main lobe. Now, we know that not all of that energy goes along the main lobe because of these diffraction effects. We also get side and grating lobes, and we can see that the energy goes off in other directions, and that's going to cause reflections from locations where an object isn't actually positioned. We get reverberation artifacts. So the sound wave can propagate down reflect off something, come back up to the transducer, but the energy doesn't, when it's reflected back up to the transducer, doesn't just stop at the transducer. Some of that energy is reflected back down again, and so we can get this reverberation effect. In the same way, if we've got an object which has significant edges, the sound wave can get trapped and reverberate backwards and forwards between those edges, each time sending some energy back up to the transducer and giving us comet tail and ring down artifacts. So the ring down artifacts are a reverberation effect that's associated with weakly attenuating objects like air bubbles, and here we can see the sound wave causing that energy to reverberate and then go back up to the transducer in a staged approach, and we can see that thin line of edges emanating down in the image on the right hand side. We can also get a comet tail artifact, so that's typically from a more strongly attenuating object, which is more of a classical form of the reverberation artifact, where we have a reverberation between two strong edges, leaching energy back up to the transducer. We also have mirror image artifacts. So our assumptions about the ray having, about the energy, having travelled along this exact straight line are not always correct. If that energy meets a strong scatterer, that energy can be scattered off in another direction, come back, and then back to the transducer. And then we can end up with mirror image artifacts, such as this liver lesion behind the diaphragm. So to summarise, in order to understand our B-mode images, we have to know how the pulse processing occurs and what that gives us and why we go through those different steps. And then once we get an image, we have to know what we're looking at. So it's not just the anatomy, we have to have a deep understanding of the artifacts that anatomy, in concert with the way that sound waves refract and change direction, combine together to give us what we see on the image display.